Okay, hi, this is Mr. Beck, and I did my project about the physics of walking. I love walking, I think it's really interesting, so I wanted to dive in what physics are actually happening when we walk. So, the first thing we have to do is define what walking is in case you don't know about it. I feel like a lot of you do know about what walking is, but maybe you don't. So, walking is one of the main ways of getting around for animals that have legs. So, something like a fish or a snake, you wouldn't really say that that walks because it doesn't really have legs. But if you have like an anteater or a giraffe or a human, they all walk because they have legs. It's typically a slower way of moving, so you can jog, which is kind of medium fast, or you can run, which is a little bit faster. And one of the main differences between walking and running, before I was kind of joking, but it is helpful to actually make a distinction between what is walking and what is running. So the main way that we're going to define the difference is when you're walking, you always have one foot that's in contact with the ground. When you're running, there's kind of this phase. You may not think about it or you may not notice it, but there's always going to be this brief moment where both of your feet have actually left the ground. You're kind of airborne, you're in the air. But when you're walking, one of your feet is actually always in contact with the ground. Like maybe you've never thought about that before, but it's kind of crazy. Like if you just stand up and do it and walk, it's like, whoa, one of your feet is always touching the ground. So here we have this picture of a person walking, and then again in running, there's always this phase where you will be in the air. But walking, always one foot is in contact with the ground. So there's a lot of physics that goes into walking, and it's all really interesting. So the first piece of physics that we learned about that applies to walking is going to be when we talked about dynamics and forces and Newton's laws. So Newton's third law is going to apply to walking because we know that this third law tells us that for every action there's an equal and opposite reaction. So when you push on the ground is then pushing on you. So you have your foot on the ground, you push on it, the ground then pushes on you. So if you look up physics of walking, there's a lot of like really simple explanations that say, okay, well you push on the ground and then the ground is propelling you forward. But that's not what happens. Like you don't slide forward because the ground is pushing on you. The ground is not propelling you forward. So that's kind of a big misconception. So you kind of have this static piece where your foot is stuck to the ground. It's not sliding backwards. So that's really what we have to say is we want to move our foot backwards. We would be sliding like that, but the ground is pushing us so that our foot does not slide. So here we have this person, he's walking, and we have this moment where he's touching the ground. And if we look at, I kind of did it there, if we're looking at what forces are acting on the foot while this person's walking, we of course we have the normal force up, we have the weight force down, and then we have this friction force that's kind of pushing to the right. They have this natural inclination for their foot to go to the left, but the ground is going to be applying this frictional force to the right. Um, and we're going to say that this is a static friction force because the foot is not actually sliding. Like over here, I have a GIF of Michael Jackson moonwalking, right? Because he's actually sliding backwards. In this case, the foot is not actually sliding. We just have this nice stationary point that our foot gets stuck on. So if we think about the third law, we can kind of identify this third law, this action and reaction pair. So we can say there's a frictional force acting on the ground by your foot. By Newton's third law, there's a frictional force on your foot by the ground. We know that friction is going to oppose this intended motion. Your foot would slide backwards. I kind of have like ice on this next slide. Your foot would slide backwards and would keep on sliding backwards, but because this friction is going to oppose this natural motion of your foot sliding backwards, so your foot won't slide backwards. And then we said, okay, well, we learned about the frictional force in class. We said that the frictional force, or the static friction force, is going to be less than or equal to the normal force times the coefficient of friction. So the coefficient of friction is a number that defines the interaction between two surfaces, and that kind of helps us explain why it's difficult to walk on ice. We know that ice has a pretty low coefficient of friction, and that means that we won't have a lot of frictional force when we're walking on ice, and because we have a low frictional force, we'll slide backwards. We won't be able to get this good plant to our foot. So the reason why this plant matters, why it matters that we actually plant our foot when we're walking, is because when we walk, we can actually think about our foot as a pendulum, or more so our foot and our leg system as an inverted pendulum. So we learned about pendulums in class, and we learned about how pendulums, they kind of have this static point, and they swing back and forth with this simple harmonic motion, and then there's this restoring force. I don't know if, yeah, whatever, I have a picture of a pendulum here. We have this restoring force. So our pendulum is going to slide back and forth along a fixed point. And we said that when we're walking, our foot is kind of making this fixed point on the ground because of this static frictional force. So our foot is actually acting like a pendulum. Our foot and then our hip joint, where we can kind of think about our center of mass being, it's kind of like this inverted pendulum, where instead of having this stationary point at the top of our string, we have this stationary point at the bottom where our foot is. So this stationary point is really important. So we can think about while we walk, our leg, our body, our hip can be modeled as an inverted pendulum. So just a pendulum that's flipped. Like, so I flipped this image of the pendulum, and let me see. I think that switches to, I should have did this. Yeah, okay, cool. So yeah, so we have this inverted pendulum that looks a lot like how our body looks when we walk. We have this stationary point, and then we have everything kind of rotating around this stationary point. So when we walk, we can actually model our legs as pendulums. So the one leg is acting as an inverted pendulum, and our other leg, the leg that's not planted, that's not stationary, is acting as a regular pendulum. It's swinging around where the hip is actually like our central point. So yeah, so we have kind of two pendulums, one that's inverted and one that is swinging around our hip joint. So yeah, we have kind of this diagram down here. Here we see, okay, we have one that's planted, so it's kind of acting as a pendulum, and then the other one is swinging around that planted leg. So we really have two pendulums. One thing that we're going to have to do when we walk is we're going to have to make our leg that's swinging, we're going to have to make it a little bit shorter by bending our knee. So that's where knees are super helpful. So we have to bend our knee so that it doesn't hit the ground. So we have two pendulums acting as one that's inverted and then one that is actually more like a regular pendulum where we actually have swinging. And so if we think about this, we said, well, we talked about pendulums before, and we said, well, pendulums, they have this defined period to them. Pendulums have this period to their simple harmonic motion. We said, okay, let's kind of disturb it from its equilibrium position, and then there will be these restoring forces that are going to try to return our pendulum, our mass, back to its equilibrium position. And we said that there's this simple harmonic motion that defines that, and that simple harmonic motion has a defined set period. So when we talked about pendulums, it all had this defined period. But in this case, we're going to see, well, we don't really have a period for when we're walking. Even though we have two pendulums, we don't really have a period. And why that's happening is because now we have this net force that is taking energy away from our system. Before, we had this nice energy transfer that was kind of dictating our simple harmonic motion. But here we have a bunch of forces that are interfering with our system. Like when you walk, we can treat our hip joint as kind of like that pendulum for our leg, the part that's swinging. But when we do that, we have muscles that are actually going to swing our leg. So when you're walking, your leg isn't just going to like limply swing forward. You actually apply a force on your leg. So you kind of have this forced pendulum, which no longer has this simple harmonic motion. So up here, I found this image of kind of the opposite. This is called like a damped pendulum. This is a pendulum where energy is taken out of the pendulum because of friction. And we see that the period, it's getting shorter each time. The period isn't this constant rate between swings. And that's because we have energy leaving our system of this pendulum. We have this damped pendulum. So here we have kind of the opposite case. We're putting energy into our system because our leg, our hip, is applying muscle, or our hip muscles are applying a force to our leg pendulum, which is changing our period. So when we're thinking about how fast we can walk, it's not dictated by a pendulum, but it is actually by the period of a pendulum equation. It's actually dictated by something else, which is really interesting. So we can predict our walking speed with actually circular motion, which is really interesting. So in class, we talked a lot about circular motion and centripetal forces, but we never really categorized pendulums in with this circular motion. And the reason for that was because when we talked about circular centripetal force or circular motion, we were looking at cases that had a constant velocity. So we said, okay, we have this a equals v squared over r, our centripetal acceleration equals v squared over r, and that was for cases that had a constant velocity. But we know that a pendulum, it doesn't have a constant velocity. In fact, there's even places on our pendulum where we have no velocity, right? We're speeding up when we're going down, and then we're slowing down when we're going up. Confusing, but we don't have a constant velocity. But nonetheless, we still have this circular path, so we know that there has to be some concepts of circular motion that apply to this pendulum. So we said that before, in order to have a centripetal motion, we need a net centripetal force, or a net force that's pointing towards the center of our circle. And we see that we totally have this when we have a pendulum. I kind of just took it at its lowest spot, but if we think about what forces we have acting on it, we're going to have the gravitational force going down, and then we'll have a force of tension pointing up, and it's tracing out this circular motion, which means that our upwards force, this centripetal force, the upwards force has to be greater than the downwards force to cause a net centripetal force, to cause this object to move in a circular path. If at this moment the tension force was equal to the gravitational force, then our ball or pendulum or whatever would just kind of keep on going off at a constant velocity. It would keep on going just like this at a constant velocity because there's no net force on it. And we know that if there's no net force acting on our object, they'll just keep on going in a straight path in a constant velocity. So in this case, because we have this kind of pendulum, we have a circular motion, which means that we have a net force in the direction towards the center of our circle, which means that our equation for the centripetal force is going to apply. And if we think about why this matters, well, we said that we can model our leg and our body as an inverted pendulum. And the same thing's going to apply. We actually have a net centripetal force that's going to be pointing downwards. That's going to dictate the speed at which we're moving. So we said before that we can model walking as an inverted pendulum. We still can use this equation, this F equals mv squared over r for our centripetal motion for our body. In this case, our body is pivoting around the foot, which is the center of our circular motion. Therefore, we have a net downward centripetal force. And we can define a tangential velocity using our circular motion equations. Like here, we could say, oh, well, we can figure out the net force. We can find the tension force, subtract the gravitational force. Now we know our net force. And we can set that equal to mv squared over r. And that v will tell us how fast is our pendulum moving at that location. We can do the same thing when we're walking, actually. We can say when we're walking, I kind of took this picture because I really liked it. I thought it had a good visual of everything, especially showing like how this person's body is moving in a centripetal motion or a circular motion. At this point, we have the weight forces going down on the foot, and then the normal force is going up. But again, we have this inverted pendulum. So instead of our net force going upwards, we have our net centripetal force, this circular path pointing downwards. So we have this circular path with the center being down here where the foot is, which means that our net centripetal force has to be downwards, which means our weight is acting in the direction of our net centripetal force. So our weight's pointing down. To figure out our net centripetal force, we have to subtract our normal force. So if we look at this, we can say our net centripetal force is our weight force minus our normal force, and we can plug it into our mv squared over r equation and figure out how fast that point is moving. So how fast is it moving along this circular path? So that's really interesting. What we can do is actually say, well, let's kind of imagine a situation where we're moving as fast as possible. Well, we said our normal force is just kind of defined as how much we have, like how much we have this reaction. So if we say that our normal force, if we make it really, really small or really, really close to zero, we can figure out our maximum walking speed by saying our normal force is really close to zero. Our gravitational force, then our weight, is just equal to mv squared over r. And we can solve and say that our maximum speed that we can walk at is equal to the square root of g divided by, g times r, where r is just the distance from your foot to your hip, or where your leg is pivoting around. So that's kind of interesting. If we kind of picture this situation where we're barely touching the ground, we'll have barely this reaction force, so we'll barely have a normal force, which means we can figure out our maximum velocity by just taking the square root of g times r. And that kind of brings up an interesting point. Like, hey, doesn't this just mean if your leg is really long, wouldn't you be a really fast walker? So if we think about that idea, we can kind of have this backed up. So I don't know if you know this or not, but there is an Olympic sport where I think they speed walk, I think it's a marathon, which is crazy. So they just speed walk, I think, the 26.2 miles, which is insane. But here's this guy who competes in it. There's this YouTube video by the Wall Street Journal. This guy walks faster than you run. And they interview this Olympic speed walker, and he says that when you plant, you have to keep your legs straight. And there's kind of a picture of him doing it in the video. I won't show you the whole video. But he keeps his legs straight. And by keeping his legs straight, he's increasing r, that distance from his foot to his hip. So he's saying, oh, well, you want to keep your legs straight, which means you're increasing r, which will increase your speed that we found based on this equation. So r goes up, the speed goes up. And of course, if you're competing in the Olympics, you want to be the fastest. You want to be the fastest speed walker. So that backs up our equation, but then that kind of begs the question, couldn't you just be a person with really long legs and then like be the best speed walker? Couldn't you then just win the Olympics if you have the longest legs? So, not necessarily. Another factor that we learned about that's going to contribute to this is going to be energy. So, one thing that we didn't really talk about but is really cool is your muscles, they expand and contract. Like whenever you do anything, you have all these muscles, you have these, I don't know too much about biology, but you have muscles that are going to expand and contract. And we can treat these muscles actually kind of like springs. So, because right, we said springs that they expand and contract, and when they have this expansion or this contraction, that stores energy. So energy is actually a huge factor when we're walking because our muscles are expanding and contracting, and therefore they're storing and then expending that energy. So when you walk, your muscles are acting like springs. They can expand or contract. When you push down, like he's doing right at this point, his muscles are going to contract, which means that he'll be able to store some of this energy. And then when he pushes off, he can actually use that elastic potential energy, turn it into the kinetic energy that we see when he's actually moving. So if you tone these muscles and you train these muscles, they'll be able to kind of give and take that energy more efficiently than somebody who doesn't have these toned muscles, who isn't trained and ready to do all this walking at this high speed. So if your muscles are developed like this guy's, you can transfer this energy better. You can transfer it to kinetic energy with less loss, without like heat loss or thermal loss. So yeah, so more energy is being conserved in his system because he's losing less energy to heat. So we talked about this idea of energy conservation. In this case, you're going to lose some energy, of course, because your body's getting hot, you're losing it to heat, you're going to lose some to the track. But by having these efficient muscles, you can better transfer energy from your muscles back into your velocity, to your kinetic energy. And then kind of like a little other things about walking. I feel like every time I go running, I get not like badly injured, but I feel like I am in pain. So like every time I run, I come back and my knees hurt, my hips hurt, my other joints hurt. So why does that happen? How can we explain why walking hurts a lot less than running? Like I could walk all day, it doesn't hurt as much, but when I run, it definitely hurts. So why is that the case? So we can think about that in terms of momentum. So when you walk, the time of contact or your stride when you're actually contacting the ground is usually a lot longer. So when you push off the ground, your foot is in contact with the ground for a longer amount of time than when you're running. And you're also pushing with less force. You're not striking the ground as hard. So if we think about your foot colliding with the ground, we can think about this as a collision. And we said that we use momentum to analyze collisions. So let's do that really quick. Let's look at this interaction between your foot and the ground as a collision. One thing that we said that affects collisions is going to be the contact time. So we said that we have this quantity called impulse, which is the change in momentum, and it's defined by our force times our time. So in this case, you're going into the ground, your velocity is kind of going downwards, it's going towards the ground. When you hit the ground, you start to move upwards. You're changing the momentum of your body. So this is really dictated by how much time you're in contact with the ground for. So if you're in contact for a longer amount of time, there's going to be less force needed to change your momentum. We talked about how impulse is the change in momentum. It's defined by force times time. So if your time is greater, your force is going to be less. Here we have kind of this diagram where we show, well, walking, you're in contact for a long amount of time. Walking is this green line. When you're jogging, you have less contact time, more force. When you're running, you have more force, less contact time. And then sprinting, a lot of force, you're really pushing into the ground with less contact time. So all of these probably have about the same change in momentum. When you're running, it may be a little bit more. But yeah, so they all have about the same change in momentum. But we see that when you're walking, you need a lot less force because that time is greater. So here we see, hey, if F is small, T is big. If F is big, then T is going to be small for the same change in momentum. And when you walk, the time of your strike is high, so the force is lowered. And then when you're walking, what did I want to do here? Oh, it just kind of shows how that happens. So your foot is kind of stretching down, so this collision is kind of spread out throughout the weight of your foot instead of just striking it really quickly. And then another last few things. This is just kind of thrown in there. I didn't do that much research about it, but I just thought it was interesting. Thinking about why our arms swing while we're walking. This is really to help with stability, and this brings in the idea of angular momentum. So our arms and legs are all really spinning around these pivot points, like our joints, like our shoulders and our hips. So because they're all spinning around some pivot point, they all have angular momentum. And we said that within a system, angular momentum has to be conserved. And in this case, when we walk, when our right leg moves forward, we see that our right arm goes backwards. When our left leg moves backwards, our left arm goes forwards. So kind of on each side of our body, we have these two pivot points that are doing opposite things. That's so weird. So they're doing opposite things, which is helping us conserve our angular momentum. One piece is getting this positive angular momentum, one's getting negative angular momentum, and they're canceling each other out so we don't have these weird rotations around our body. So this keeps us from just getting extra rotations that would act to conserve angular momentum. So again, I didn't research that too much, but it was just a quick little thing that I saw towards the end. Some cool applications of this, like why all these ideas matter. The human body is really complicated. Trying to model the human body is very difficult. And walking it's crazy how complicated walking is. Like there's a lot that goes into it. And the more that we understand walking, the better we can create a model for how humans work and how they walk. And the reason why this matters is because we're in this age where we have so much technology and we want to do things with this technology. So building robots that can kind of mimic what humans do is something that's important, something that we're kind of building towards. I'm sure you guys see these videos from like Boston Dynamics all the time. They have like the four-legged robots that kind of look like dogs, kind of, but they also have these two-legged bipedal robots, and they walk. And in order to get them to walk, and they do a lot of crazy things. Like you see these videos where people like push them and then they like catch themselves from falling down, or they do flips. Here they are traversing like a pretty difficult environment to traverse. And if we can understand how walking works, we can program these robots to mimic that, and then they can kind of do the things that humans can do, which is interesting. Another thing that I saw a little bit ago that was really cool is this. I don't understand too much about artificial intelligence, but I think it's this group at Google kind of made this little model of this person. They didn't give them any instructions. They just said go from point A to point B and didn't teach the model how to walk at all. And this is really interesting because it used the artificial intelligence figured out how to walk. So it does it in a weird way. It's kind of thinking like, hey, this doesn't super look like how humans do it, but it's pretty close. It's a pretty close approximation to how humans walk in the most efficient way possible. So that just kind of shows some cool, like evolutionarily, we did a pretty good job developing these legs and these arms and the way that we move to maximize the efficiency of walking. If this computer decided, hey, this is the most efficient way for me to get from point A to B, this is how I'm going to walk, it's kind of cool to see that we do the same thing. It doesn't know what humans are. It's not mimicking walking. It just decided, based on the constraints I have, this is how I'm going to walk, which is kind of neat. So that's my little presentation about the physics of walking. Thanks.